Last class we learnt about the concept of VBT, wherein we learnt about the example of formation of oxygen molecule. Now in this session, let us learn about the concept of hybridization. What is hybridization? It is the process of mixing up of atomic orbitals. Which are these atomic orbitals which are undergoing the mixing up? And when will this happen? Whenever there is a bond formation taking place involving polyatoms, meaning many atoms are participating to form one molecule. In that cases, in one of the central atom where all other atoms are going to attach, in that, in order to accommodate the coming atoms, it will undergo a process. The central atom will undergo a process called hybridization. What is hybridization? It is a process of mixing up of the atomic orbitals. Which atomic orbitals? Again, the focus point is for the valence atomic orbitals. And what should the condition be for mixing up? They would be having half-filled orbitals. So, the point of focus is that for undergoing the process of hybridization, there is involvement of the valence atomic orbitals and they are all half-filled valence atomic orbitals. Now, why are they undergoing this mixing up? As I told you earlier, they are undergoing bond formation in order to accommodate the coming atoms to form a new molecule. This change is being done within an atom. Now we'll understand about the different types of hybridization. There are many types of hybridization. Important among them are SP3 hybridization, SP2 hybridization, then SP hybridization. So therefore, these three are the ones we are going to discuss in the coming lessons. SP3 hybridization, SP2 hybridization, SP hybridization. As we can see here with SP3, there is involvement of S atomic orbital and involvement of P atomic orbitals, and in this case all the three P atomic orbitals are undergoing the process of hybridization. That means they are undergoing the process of mixing. As we know, between S and P orbitals there is energy difference. S orbital of the valence shell will be having less energy than the P orbital of the same valence shell. Valence shells are the ones which are going to undergo the process of hybridization. So the focus point is always with respect to the valence shell orbitals, and S orbital will be having less energy than the orbitals of P. And which are the three orbitals of P are we talking with respect to? All the Px orbital, Py orbital, Pz orbital of the valence shell of an atom will be undergoing mixing with the S orbital of the valence shell. That means they are the orbital present in the same shell. There is energy difference between S and P orbitals, and the product obtained by the process of hybridization are called the hybrid orbitals. The product obtained by the process of hybridization are called hybrid orbitals, and all the hybrid orbitals formed will be having same amount of energy. This is another focus point. So all the participating atomic orbitals, though they might be having difference in the energy, the product obtained by them, which are called as the hybrid orbitals, will be having same amount of energy. There is no energy difference in the hybrid orbitals formed, and the number of hybrid orbitals formed depends on the number of atomic orbitals participating for the process of hybridization. Now we can see in this example of SP3 hybridization, there is participation of one of the s orbital and all the 3 p orbitals. So totally 1, 2, 3, 4. 4 atomic orbitals are participating for the process of hybridization. How many hybrid orbitals will we be obtaining? Equal number of hybrid orbitals will be formed. Equal number of the atomic orbitals which are undergoing the process of hybridization. The same number of hybrid orbitals will be formed. That means in this case of sp3 hybridization, it will form 4 hybrid orbitals. In all the 4 hybrid orbitals, they will be possessing same amount of energy. All of them would be having same amount of energy. And each hybrid orbital, in the case of sp3 hybridization, is called by the name as sp3 hybrid orbitals. Means how many sp3 hybrid orbitals are obtained for us? 4 sp3 hybrid orbitals are obtained, and all the 4 sp3 hybrid orbitals will be having same amount of energy. So by understanding this, let us get into some more details. Before which, let's have a look at these two. sp2. Now you can understand what do we mean by sp2. sp2 means there is participation of one of the s orbital and 2 of the p orbitals. Which 2 p orbitals will be participating? Px and py. How many hybrid orbitals will be obtained? There is participation of 3 atomic orbitals. So it will yield us 3 hybrid orbitals. Similarly, sp hybridization, there is involvement of 2 of the atomic orbital, one s orbital and one of the p orbitals. So how many hybrid orbitals will be obtained? 2 hybrid orbitals will be obtained, and both the hybrid orbitals will be having same amount of energy. By saying that, let's continue with the concept of sp3 hybridization. Let us also learn this concept with an example. Now let us see how the mixing up actually happens. We have the s orbital. S orbital, as we know, is spherical in shape. So when we are writing in 2-dimensional figure, this is how we can represent the spherical shape. So s orbital is undergoing mixing up with 3 of the p atomic orbitals. Px, then we have py, and then we have pz. So we have the participation of one of the s atomic orbital, px atomic orbital, py atomic orbital, pz atomic orbitals. So all of the p orbitals are dumbbell shaped but are orienting along different axes. So they all combine. They all will undergo the process of hybridization. Now, what will be the product obtained? We will land up in the formation of hybrid orbitals. So, how many hybrid orbitals will we be obtaining? 4. Each one is called by the name as sp3 hybrid orbitals. We will land up in the formation of 4 sp3 hybrid orbitals, and these would be the atomic orbitals of the valence shell. and they would be containing one electron each. And where would these electrons be? In the hybrid orbitals. Now each of the sp3 hybrid orbitals will be containing one electron. These are the electrons that would be present in this atomic orbitals, which is now present in the hybrid orbitals. Though there is energy difference between s and p orbitals, the hybrid orbitals obtained will not have any difference in the amount of energy. They are all called degenerate orbitals, and they will be taking the shape of a tetrahedron like this, and they will maintain a bond angle of 109 degree 28 minutes. This is standard. Whenever an atom undergoes sp3 hybridization, in normal cases, they will possess a bond angle of 109 degree 28 minutes. Now, let us take up the example for the sp3 hybridization. Example case is methane. We are going to study about the formation of methane. And what is the molecular formula of methane? As we know, methane is the first member of alkane. Its molecular formula is CH4. So what can we see here? There is one carbon atom which is bounded with 4 hydrogen atoms. How will this be undergoing the process of sp3 hybridization? Let us have a look at it. This carbon atom is having atomic number as 6 and its electronic configuration in the ground state. That means in the normal state. How will be its configuration? 1s2, 2s2 and 2p2. This is how it will be present. All the 6 electrons are placed like this. 1s2, 2s2, 2p2. Let me just write the orbital picture so that we will have a better understanding. Now these are 2px, 2py and 2pz. How many electrons are to be filled? 2 electrons. So 2px1, 2py1 and 2pz is having no electron. So 2pz 0. Now as the hydrogen atoms approach the carbon atom gets excited because of the release of the energy due to the approach of this hydrogen atom towards it. Now the configuration changes. So let us see what is the excited state electronic configuration of the carbon atom. Carbon atomic number remains the same. Now what happens is that due to excitation, one of the electron from the 2s energy level will jump to 2pz energy level. So let us see how the configuration will be. 1s2. Now because this electron jumps here we have 2s1 and how many will be there? One more comes over here. So 2p3. Let us write the orbital picture. So with 2s electrons are filled. So what do we have? 2px, 2py and 2pz. How are these 3 electrons? 2px1, 2py1, 2pz1. So therefore all the valence orbitals, which are the valence orbital for the carbon? 2s and 2p. All of these valence orbitals are half-filled, means they are containing 1 electron each. This is the reason why the carbon atom is tetravalent. It's tetravalent because each of its valence orbital is containing one electron and it can accommodate in each of the atomic orbitals one more electron. So therefore the combining capacity of the carbon is 4. So therefore we call it as tetravalent. Now these atomic orbitals 2s, 2px, 2py, 2pz, they undergo mixing up. That means they are undergoing SP3 hybridization. They are undergoing SP3 hybridization. Now, because they undergo SP3 hybridization, what would be the product formed? They will be forming 4 SP3 hybrid orbitals. Now, let us say this is the 2s of carbon atom, 2px, 2py and 2pz. So they are orienting along different axes. 2s and 2p are having difference in the amount of energy. But please remember, there is no difference in the energy between 2px and 2py or 2py and 2pz. They are all having same amount of energy. But energy difference is existing only between 2s and 2p orbitals. Now they have all undergone mixing up or hybridization, resulting in the formation of 4 sp3 hybrid orbitals. So the central carbon atom has undergone this much of change. Now carbon atom is ready to undergo bond formation with the hydrogen atoms. Now let us see how this actually happens. Now hydrogen has got the atomic number as 1 and its electronic configuration is 1s1. What is the shape of this orbital? S orbital, as we know, is spherical in shape. So like this, how many hydrogen atoms are there? According to the molecular formula of methane, we have 4 atoms of hydrogen. So 4 such spherical orbitals will be coming and they will come and overlap head on with each of this sp3 hybrid orbitals. And also remember, these spherical orbitals of hydrogen is containing 1 electron each. They are containing 1 electron. So what happens now? At each sp3 hybrid orbitals level, there is overlapping of the spherical orbitals of the hydrogen. And now they are undergoing head-on overlapping, and if they undergo head-on overlapping, what kind of bond is formed? Yes, we know that it results in the formation of sigma type of covalent bond. Why is it sigma type of covalent bond? It's because of the head-on overlapping. So with each of the sp3 hybrid orbitals, there is overlapping of the hydrogen atom, resulting in the formation of sigma type of covalent bond. And what is the bond angle? As has been discussed earlier, the bond angle is 109 degree 28 minutes. What is the shape of the molecule? Tetrahedron. Now finally, how will this molecule be with this shape? So this is the carbon atom and each corner is occupied by the hydrogen atom. What's the bond angle? 109 degree 28 minutes. And what is the type of bond? Sigma bond. So how many sigma bonds are there? 4 sigma bonds are there. So the points to remember here is shape of the molecule is tetrahedron. Then bond angle is 109 degree 28 minutes. And how many sigma bonds are there? 4 sigma bonds are there. So this is how molecule of methane is formed. In a similar way, ethane molecule is also formed. Now in case of ethane, the change that you need to remember is whatever we observed with respect to one carbon atom in methane, the same kind of hybridization would be happening with 2 carbon atoms in case of ethane, because ethane is having a molecular formula as C2H6. So now in this case what happens is, of the 4 SP3 hybrid orbitals, 1 SP3 hybrid orbitals from each carbon atom is utilized for head-on overlapping between the carbon atoms to result in the formation of sigma bond. So between one carbon and another carbon there is a sigma bond, and each carbon in turn, because if one sp3 hybrid orbital is utilized, how many more sp3 hybrid orbitals are still remaining? 1, 2, 3. 3 of the sp3 hybrid orbitals would be remaining. Now each of these sp3 hybrid orbitals in case of ethane would be bonding with the hydrogen, as we can see here, resulting in the formation of sigma type of covalent bond, because it is a head-on overlapping. So therefore each carbon atom in turn is linked with 3 of the hydrogen atom, and hydrogen atom being spherical in shape can always undergo only sigma type of bond formation because of head-on overlapping. So therefore this is how the ethane molecule would be by undergoing the process of sp3 hybridization.